So welcome to the new experiment, that is to simulate the operation of a single phase full wave control converter using SCR. As you know that the SCR is a semi-control device. You can easily control the turning on off of the SCR. But if you want to turn off the SCR, then for turning off of the SCR, that is a commutation, you will be requiring auxiliary SCR, inductor and the capacitor. You will be requiring the oscillatory circuit to create an artificial zero. This has been already discussed in the lectures that to turn off the SCR, two conditions are very important. The first, that you will have to reverse bias. You will have to provide a reverse bias across the SCR and to reduce the anode current value below the holding current. Only in that condition you can proudly say that the SCRs will be turned off. Again, the commutation will be classified into some I think class A to class F. Class F is a natural commutation. So the natural commutation means line commutation, that is the zero crossing. At the zero crossing, you can say the anode current value is below the holding current, and because of that, the SCRs will be turned off. But the force commutation will be of class B, class D, and class C. So that will come under the force commutation, and load commutation is of the class A. So we will try to analyze the waveform when you connect a resistive load and the RL type of load. RL type of load basically is an induction motor type of load, and when you are saying resistive type of load, it means a lamp load or a lighting load is there. So the when you will solve, when you will integrate and solve the value for the average output voltage, this 2 Vm by pi into cos alpha will come into a picture. So this is some theory. If you just refer it out, then you will get the feel of it. So now we will shift our attention towards the PSIM. So again, this is a PSIM interface. We'll try to simulate. So this is a single phase. It means that there are two legs. Two legs are there. Two legs having four switches. This is the upper switch and this one is the lower switch. Again, this will be in the bridge configuration. That means the four SCRs will be required, and to this we have connected a resistive load. And again, there is a step down transformer. You can call it as okay. So in this case, isolation transformer has been used. You can see the number of turns on the primary and on the secondary. They are equal. So when such is the case, when such arrangement has been done, you can term this as the isolation transformer. Basically, it is used to isolate the input side from the output side. It means that you have taken the SCRs of a low value ratings. Okay, so we will try to simulate and then we'll come back to this PDF for the verification. Okay, for cross checking. Okay, so now again you will be requiring input voltage source. So where is that? Okay, so we have connected. Then you require the SCRs. For that element, go to power, then SCR, okay, switches, then the thyristor will be there. Okay, so rectify, right click, so you will get the proper, yeah, proper orientation. Now this is again the SCR. Okay, so four SCRs will be connected. This should be in the line. Okay, so now now the connection. Now we will require a connection, but before that, a resistive load. We will connect resistive load. Okay, so by using a wire tool, you will have to connect this. This is the SCR. Okay, this is not connected properly. This is a strong connection has been made. Again, okay, so the load side is done. The load side has been done. Okay, I think we require some current also. We require a current, so we need to open this. Let us take this. I don't know. For current, you will be required because you need to find the load current also. So this is the thing. So now in this week, you can easily make the connection. Again, this voltage source between the two legs. We will check the Okay, we'll check the amplitude of the voltage source. I think we have not varied the amplitude. So I think this is 312.5. You can name it as Vn, and you will have to change the frequency as 50 Hertz. Okay, so now these are the ideal switches. Okay, we'll keep the load as 10 ohms only. The current will be, attenuated only. The current will be attenuated by that much resistance because I will be equal to V upon R. The resistance has been connected onto the output side, so you can easily apply the Ohm's law. Now for this you require, right, a current probe is needed. So this is the current probe. Okay. Similarly, you will be requiring a voltage probe. So, okay. I am using a voltage probe between the two ends. You can go for a node to ground also. That is your choice. Okay, this has been connected. The connection has been made. The current is going to enter into the load. That's why we will have made the connection. We have placed this ammeter in this fashion. Okay, so now just a minute. The connection established. Okay, so this is the way, right. So now you will have to provide the gating pulses because as I have already mentioned that you can easily control the turning on off of the SCR. So this T1 and T2 will be forward biased for the positive half and T3 and T4 will be turned on for the will be forward biased for the negative half. So the gating pulses to this T1 and T2 will remain same, and similarly you will have to provide the same gating pulses to this T3 and T4. So this T1 and T2, again I am repeating, this T1 T2 will be having the same gating pulse. So okay, so for gating pulse, gating block will be used. Okay, I will try just a minute. Okay, so this is Okay, the connection has been made. Right, we will provide the gating pulse to a gate. Now, as I told you that the both will turn on simultaneously. Okay, so we will place a wire. Okay, just a minute. Right. It means that this T1 and T2 will be forward bias, and on the application of the gate pulse, this will enter into the conduction. Okay. So now the frequency is 50 hertz and you are having switching point will provide this is to provide the firing angle. Now suppose if your firing angle is 30 degree because you can have the range of firing angle is between 0 to 180. So you can have the firing angle at any given angle that is 30, 45. So what I can say that will give 45 degree. We will give as a 45 degree. Okay. So I think this is okay for this T1 and T2. Now similarly this T3 and T4. Okay, just a minute, right? Now connection should be done. Okay, just a minute. Okay, so everything is right. I think this was not properly connected. Now the T3 and T4 both will be having the same gating pulse. Okay, just a bit. I don't know why I have put all these wires. But okay, let it be, not an issue. Okay, so now we will do some variation here. The frequency will be 50 hertz, and this T3 and T4 are going to be operated in the negative half. So the positive half will be from 0 to 180, and negative half will be from 180 to 360 degree. So the 45 degree you have at 45 degree is the firing angle for T1 and T2. So 45 plus 180, that will be 225, and right. So this will be 360 degree. because you can see here that this is the 45 degree. You have given the alpha, that is the gating pulses at this angle, because the one cycle will be of 360 degree. So the first positive half will be from 0 to 180 degree, and second half is from 180 to 360 degree. So depending on, we have placed the values of firing angle, or you can say we have placed the values of switching points. Okay, so now I think everything is set. We will display this. That is the input. Okay, not an issue. We will display this because we need to understand what should be the waveform. Then this one is out. Okay, this is for the resistive load. I will try to see whether we have achieved or not. But before that, simulation control, just like your power GUI. I think this is sufficient. So now the run simulation. This is the demo version. So you can see input voltage. This is okay. Now for splitting the window, this input voltage is done. So this is the output voltage. Okay. And we need to find the current also. Current is this much. Okay. So resistive load, voltage and current will be in same phase. You can see here voltage and current will be in same phase. This is the same waveform which we have obtained. Okay, so I think this is okay. So now you need to do the simulation for the RL type of load. Okay, so we'll copy all this. We'll copy and we'll try to reduce the hour time. Okay, we'll try to copy this. Now this is the thing. Okay, we'll make this as I1 and this one as I2. Okay, this one as I2. Everything is right. What is the value? That is V output 1. Right, this is V input 1. Then this one is I, right, it is, let it be. Okay, so now this simulation should be done for the RL type of load. So okay, some cutting should be there. RL type of load, I don't know what is the value, but still I will try to, I don't the value of right, but we will try to assume the value. Now this one is what we can take as 0.05, let it be. We'll try to check whether we have got the result or not. Okay, now this one is V in. Okay, so V in, this is okay, 50 hertz waveform, and V output, this is also okay. I think something has not been done. Just a minute. I will do the run simulation. So, okay, V in, and this one is V out one. Okay, it has not been rectified properly. Then the current value, that is the I2. Okay, now we will do something. We will try to vary the value of the inductor as 10 millihenry, or light 1 2 3, that is 10 a to the power of minus 3, or you can say 100 millihenry we can write. Okay, 100 millihenry, just a minute. So v1, v in and v out. Right, so finally we have got something which we were expecting, and now we will try to find the this I2 also. The current also we need to find. Just a minute, we will remove this I1. So from here, the variables for display. Now suppose if you have selected the variable, you can also remove it. Okay, so this is right. You can see that you are operating in the continuous conduction mode. You are operating in the continuous conduction mode. That's why your current will remain. Yeah, it will reach to a steady state value, because of the demo version, we will not be able to see the to the steady state value, but you can see that this is going to enter into a steady state in a near in a near time. So this is all about the RL load. So what I can do that I will again simulate this and try to obtain all the waveforms in one window. So okay, so V in and V out. This is the thing. Then we will try to plot the current. As you can see the current, the load is resistive, voltage and current will be in same phase. Okay, so now for V in, V out for RL type of load. Okay, this is also okay. Now the current for this is this. Okay, so you can see here in this way, you can simulate the waveforms for the R and the RL type of load. Now, you can also calculate the voltage across a switch and the current through a switch. So whatever waveform you want to obtain, that can be easily checked using the voltage probe and the current probe. This is all about for today's experiment. We'll meet in the next video with a new experiment. Thanks a lot for watching this.